digital world. So everything is digital now. We are sending, receiving and processing, and everything is in digital. Electronic gadgets, which is either sending, receiving or processing digital data, is using a small device which is called the analog to digital converter and also digital to analog converter. So this video we are going to discuss about analog to digital converter or ADC. Okay. So an analog to digital converter, from the name itself it is clear, it is going to convert an analog signal to digital signal. So why we are going for ADCs? Why we can't process analog signal? Because analog signal is more noisy and it is also very difficult to process. While considering digital signals, they are easy to transmit, they are easy to process, easy to store, and also they are easy to handle. And also they are very much noise free. So that is why we are going for digital signals. So what an ADC is doing is, it is going to take an analog signal, because we know that in the real world everything is in analog. So an analog signal is taken by the ADC and it is going to convert this analog signal to a digital form. So an analog signal is taken by the ADC and it is converting this analog signal to digital form. So the input is analog and the output is digital. So this is the in and this is the out. Okay, so this is actually the primary role of an ADC and how this ADC is doing this process or this conversion. So ADC mainly uses two steps for achieving the process of digitization. That is the sampling and the quantizing step. So the first step is sampling the signal and the second step is quantizing the signal. In the first step, what it is doing is, we know that analog signal is continuous in time and continuous in amplitude. So in the first step, that is in the sampling step, it is going to discretize the time. That is, we know the analog signal is continuous in time and continuous in amplitude. So in the first step, that is in the sampling step, so the sampling step, the continuous time is converted into discrete time. Okay, in the next step, that is in the quantizing step, it is going to discretize the amplitude also. So at the end of the second step, that is at the end of the quantizing step, we will be getting a digital representation of our corresponding analog signal. First, let us discuss in detail about the sampling. Okay, so I am going to take a continuous time signal here. This continuous time signal, I am going to, that is, it is having continuous time. I am only considering time here. So it is having values at all instants of time. I am going to take only discrete time instants. Okay, so like this. That is, I am going to take this 1, 2, 3 only from this portion. Then this 4 and 5 from this portion and this 7 and 8 from this portion. So these are my samples. So my output will look like, okay, I am going to draw only this much. My output will look like, that is at 1, 2 and 3, 4 and 5, 7 and 8. Okay. So if you take this much portion of the signal, the sample signal will look like this. So this is the sampled signal. Okay, so this is a sample signal now. So we have to convert that continuous time to discrete time. So the difference is that this is continuous in time, this is only discrete. That is, only discrete values are present. So we know that after digitizing the signal, so after the signal is digitized, we have to reconstruct it back to the analog form to actually for real world applications. So we have to reconstruct the signal which is being digitized. So in order to have a reconstruction, that is perfect reconstruction, while sampling we have to follow certain criteria. So that is, while selecting the samples, we have to follow certain criteria in order to perfectly reconstruct this signal. So this is actually the sample signal. So after the quantizing, we get a digital signal. So in order to reconstruct the digital signal back to the analog form, we have to follow certain criteria while sampling the signal, and that is called nothing but the Nyquist criteria. So that is a famous topic, Nyquist criteria. It's a very famous topic in digital electronic and digital signal processing, which is the Nyquist criteria. So if we are sampling the signal by following the Nyquist criteria only, then we can reconstruct the digital signal back to your continuous time and continuous amplitude signal. So what is Nyquist criteria? Nyquist criteria states that the sampling frequency Fs should be greater than or equal to twice the bandwidth. So this is the Nyquist criteria. That is, the sampling frequency which you are selecting to sample the signal should be greater than twice the bandwidth of your original signal. Okay, so this is the Nyquist criteria. So only if you are sampling at this frequency, then only you can perfectly reconstruct your signal back to your original analog signal. Actually, reconstructing your original signal is not applicable because obviously reconstruction is involved with some loss, because whenever you are digitizing a signal, an analog signal, it is involved with some loss. But if you follow the Nyquist criteria, then you can reconstruct the almost similar signal to your analog signal. So if you are not following the Nyquist criteria, then the reconstruction is not possible. So while sampling, you should follow the Nyquist criteria, which is given as Fs. Your sampling frequency should be greater than or equal to twice the bandwidth of your signal. So at the end of the sampling stage, there is a sample and hold circuit to keep the sample signal constant so that the ADC can perform quantizing. That is a step 2. So we are going for step 2. So before moving to step 2, that is the quantizing step, there are certain things you should understand. First one is the number of bits of an ADC. Number of bits of ADC. So this number of bits indicates the number of bits with which the ADC can represent the digital representation. So you know that digital representation is involved with binary numbers. So in how many number of binary bits the ADC can represent the digital output, that is called the number of bits. Okay, so if n is the number of bits of an ADC, then the quantizing levels over the signal is quantized to 2 raised to n levels. 2 raised to n represent the number of levels to which the signal is quantized. So this thing you should understand. So if n is the number of bits of a ADC, then 2 raised to n is the number of quantizing levels. So if n is equal to 2, then 2 raised to 2, that is 4. That is, you are going to quantize your signal to 4 levels. So that is quantization levels. Next, the third thing you should understand is resolution. So resolution is defined as the minimum change in the input voltage that the ADC can detect. So resolution is defined like that, and it is given by the equation VFS by 2 raised to n. Now what is VFS? That is the full scale voltage. By 2 raised to n. Okay. Now, how can you find out full scale voltage? So this full scale voltage is again given by V max minus V minimum. So while explaining the quantization, we'll see what is full scale voltage. So resolution is given by V max minus V minimum by 2 raised to n. So this is actually resolution. So these three things you should understand. First one is the number of bits of the ADC. That is, how many number of bits will the digital representation have. That is, each value will be represented using n bits. So if I'm going to represent a voltage 0.5, then if the number of bits is 2, then this digital representation will be having two values, which can be either 00, 01, 10 or 11. So that is, each value will be having two number of bits. So if n is the number of bits, then each value of the ADC, each digital value will be having 2 bits. In general case, n is the number of bits, then it will be having n number of bits for each digital value. Again, second one is the quantization levels. That is, to how many number of levels we are going to quantize a signal. That is given by 2 raised to n. So if n is the number of bits, then 2 raised to n is the number of quantization levels. Okay, the third thing, which is a very important thing, that is the resolution of an ADC. Resolution is defined as the minimum change in input voltage that the ADC can detect. Okay, and it is given by Vmax minus Vminimum by 2 raised to n. So these three things is very much important while studying or understanding the concept of ADC. Here I am selecting an ADC with a number of bits equal to 2. So my ADC is a 2-bit ADC. So here my 2-bit ADC will be having a quantization levels of 2 raised to n. So if my ADC is n, then number of levels to which I am going to quantize the signal is 2 raised to n. That is, if I am using a 2-bit ADC, then if n equal to 2, so 2 raised to n equal to 2 raised to 2, which is equal to 4. So I am going to quantize the signal in 4 levels. Okay, so that is understood now. Also, we have defined resolution as Vmax minus Vminimum by 2 raised to n. So here Vmax is 1 volt. So here the Vmaximum equal to 1 volt and Vminimum equal to minus 1 volt. So what is the resolution? So resolution is equal to Vmax minus Vminimum is 1 minus minus 1 by 2 raised to n is 4. That is, 1 minus minus 1 is 2. 2 by 4. So here the resolution equal to 1 by 2, that is equal to 0.5 volt. So this is the resolution. So what is actually resolution? Resolution is the minimum change in voltage that the ADC can detect. So if the signal is changing to 0.5 volt or more, then the ADC will detect the change. Okay, so the resolution is here is 0.5 volt and I am going to quantize the signal to 4 levels. So I am going to select my quantization levels here. So that is 0, then 0.5 because the resolution is 0.5, then minus 0.5 and minus 1. So these 4 levels I am going to quantize the signal. And since the number of bits is 2, the values will be, digital values will be 00, 01, 10 and 11. So these are the 4 quantization levels. These blue color lines represent the quantization levels. Minus 1 volt is represented as 00, minus 0.5 volt is represented as 01, 0 volt is represented as 10, 0.5 volt is represented as 11. So these 4 levels are the quantization levels of this particular ADC. Okay, so now I have already selected the samples of my signal. So this is my original analog signal and I have selected certain samples. That is, I have already sampled my signal. So my samples are at 0. This value is at 0.7 volt, 1 volt, again 0.7, 0, again minus 0.7, minus 1 and minus 0.7 and 0. So these pink color lines are the samples which I have selected or which is obtained by the process of sampling. Let's see how the quantized signal will look like. Okay, so first let's see about this sample. So it is at 0. So let's select the same level because we have already a 1 0. So we have a quantization level at 0. So it will look like this. Again, while considering this sample at this point, the value is at 0.7 volt. So in order to quantize this 0.7 volt, we have to select the nearest value. So 0.7 is nearer to this quantization level. So we are going to select the quantization level as 0.5 volt or the value 11. Okay. So again, for this particular sample, the value is again closer to 0.5 volt. So we are going to select that again, because we have the quantization levels at 0, 0, 0, 1, 1, 0 and 1, 1, and we have to select here the value is at 1 volt, right? And the value or the quantization level closer to this value is this 0.5 volt. So we are selecting this. So again this. Now taking the case of this 0.7 volt, again we are going to select this value. Now coming down. Okay. So next value or the next sample is at 0. So we have a quantization level at 0 volt. So select that. Okay. The next sample is at minus 0.7. So we have a quantization level at minus 0.5. So select the minus 0.5. Okay. Now the next sample value is at minus 1. Okay, we already have a quantization level at minus 1. So we are going to select the minus 1 quantization level. The next sample is at minus 0.7. The closer value to minus 0.7 is minus 0.5. Okay, so we are selecting that. Okay, so this much of samples we have selected. So the quantized signal will look like this. Okay, if the next sample is at 0, then it will look like this. Okay. So this red colored signal is actually the quantized signal. So we have obtained the digital representation of the analog signal. Okay. So here this blue colored signal is my original signal and this red colored signal is my sampled and quantized signal. That is, this is my digital representation and it will be having a value of, here the value is 0. So here the digital representation for the 0 level is 1 0, then 1 1, 1 1, again 1 0, then 0 1, 0 0, 0 1 and finally 1 0. Okay, so this is how quantization is done. So what is actually we are doing in quantization? We are going to select the closest value for the original input signal. So here the sample is having a value of 0.7 and we are going to select the closest value for that 0.7, which is 0.5 here. So 0.7 volt is closer to 0.5 volt and we are going to quantize this 0.7 volt to 0.5 volt. Okay, and hence we are selecting this level and correspondingly we are selecting all other levels. So first we are going to analyze what are the quantization levels. So in order to quantize a signal, we have to first identify what is the number of bits. So if we get the number of bits as n, then we have to find how many levels are present in quantization, and it is obtained by 2 raised to n. And if 2 raised to n corresponds to 3 levels or 4 levels, then the signal is being quantized in 3 levels or 4 levels. And then we have to find out what is the resolution, that is what is the difference or delta for each level. So here, that is Resolution is the minimum change in the voltage of input that the ADC can identify. So here the ADC will identify a change of 0.5 volt minimum. So if the change is greater than 0.5 volt or if the change is 0.5 volt, then the ADC will identify it. Okay, so we are going to define levels of difference 0.5. Okay, so -1, then 0.5 minus 0.5, 0 plus 0.5. So each quantization level will have a width of value 0.5 or the resolution. Okay, so then we have to optimize this analog value to that quantization level, or we have to map the analog value to that quantization level, and hence we will get the digital representation of the signal. So this is actually quantization. I hope it is very much clear. So quantization is actually a process in which error is occurring because we are going to leave out some of the values. So here if you consider the value is originally, or the real value is at 0.7, but we are going to optimize the signal to 0.5. Okay, again here the value is at 1, but we are taking only 0.5. Here also the value is 0.7, we are taking only 0.5. So there is a difference of how much voltage. Let's see, for this case, that is for the 0.7 case, so the original signal is having a voltage of 0.7 and the quantized signal is having a voltage of 0.5. So what is the difference? There is a difference of 0.2 volt. Correct. So a 0.2 volt we are going to ignore. Even though the actual value is 0.7, we are taking only 0.5. So this is actually an error. And so I'll make it more clear. That is, even though the value of the signal is originally at 0.7, we are going to consider that. So in order to digitize the signal, we are going to consider that the value of the signal is present at the level 0.5. So we are ignoring this 0.2 volt. So this 0.2 volt is actually the quantization error. So for this particular sample itself, we are making an error of 0.2 volt. So while quantizing this entire signal, we are losing out lot of values. So this whole together will be said as the quantization error. So at each point we are losing out, or we are reducing or deducting some values, since we are rounding off the value to the nearest quantization levels. So this error is called quantization error. So this error is involved while we are going to digitize a signal using an ADC. Okay. So that is quantization. In this video, we have discussed the concept of analog to digital converter. We have discussed what is sampling, what is quantizing, what is quantization error, what is resolution, number of bits, etc. So we have covered all the basic topics related to analog to digital converter. I really hope you enjoyed watching the video. If you gained some knowledge with this video, please try to share this knowledge with your friends and family. And don't forget to subscribe to the channel. Thank you.